All right, thank you very much for giving me the opportunity to speak about this work, which is more than 8 years old, but I still feel like this work are related to many people's interests. So, okay, so I wrote something here just to test that if the size of the letter is okay. Can you really see it? Okay. What about this smaller one? Okay, I just want to. Okay, the reason I want to do that is because today I want to give a talk a very similar. More like a mathematician's tradition. I want to write every important thing on the board so that I try to avoid I will avoid to erase too much. So I want to write it more densely. Okay, so that I won't erase it. So you can see the logical flow is quite continuous. Okay, so if I erase it, you will forget what. And another reason is that some people complain that this work is a little too abstract. So it's really my hope today that I can slow down and make sure everybody can follow me. Okay. All right, let's start. Okay. So I will start with a very fundamental result that I have learned when I enter the field. So it says that the 2+. Oh, by the way, I will use TO to represent topological order, just for simplicity. Okay, so 2+1D topological order can be completely characterized by a pair. And this C, the first C is a multi-tensor category of Wilson lines. If you were high-energy people, you like to use Wilson line. If you're condensed matter people, you want to use any else. Okay, the small c is the character-centered charge. Okay, so let's see what's the structure in the multi-tensor category. Okay, it says that in the spatial dimension, 2D spatial dimension, you can have some anyons. Okay. In 3D, there will be a Wilson line. But then you can fuse them. That give you a tensor product. Then you can also braid them like this. So it's a braided tensor category. But if you look closer, let me make it more precise, because today we're going to go over this one more time. So we're going to do slowly here. What's the object in C? C is their objects, ABC, using small letter. They label anyons. Oh, this has been erased. They label anyons. Okay, and or Wilson lines. Okay, there are also Helm space for each pair of objects. There is a Helm space. This space is a space of instanton, right? Because they localize, because they localized in space-time, and it is a finite dimensional vector space. Okay, so that means dimension of this. That's inside the definition of multi-tensor category. Oh, by the way, maybe in the future, I'm going to abbreviate the multi-tensor category by MTC. All right. And there are also a trivial instanton inside of each Helm AA. And there is another data defining the category is the compositional morphisms. So the compositional morphisms from a physical point of view is very obvious. So you have some instanton here. You just fuse them in the time. This is time direction, okay? Just fuse them along the time direction. That gives you a composition map, okay? All right, that's the basic data of category. We're gonna see this one more time in our when we analyze what happened on the gapless boundary today. Okay, so but I want to make a very important comment is that this pair summarizes all the microscopic observable survive in the long wavelength limit. Okay, because for what is strange about this type of topological physics is it's gapped. So at a low temperature, all the correlation function is exponentially decay. So in the long wavelength limit, there's no observable seems. So this space from traditional condensed matter point of view is trivial because it does not respond because correlation function all exponential decay. If I used using different language, I would say they do not respond to any external probe. So it seems that this type of phase is supposed to be trivial, but it turned out it's a great discovery in 80s that this phase, the seemingly trivial phase, is actually non-trivial. Okay, and there are observables given by anyons and the character-centered charge. Okay, yes. When you say topological, which definition of topological are you using? I'm using it is a gapped phase at 0 temperature without symmetry. Okay, so if we use that definition, is there or is more like a gap Yeah, depends on how rigorous you are. Like I'm a mathematician, I always take a conjecture, but for most physicists, they're a theorem to some extent. Yeah. I know. Yeah. I like to put. Okay, let's put a question mark here. Conjecture. So everything I wrote today is conjecture. Yeah. Okay. You are so rigorous. I'm surprised because I'm a mathematician. I read a unitary in the paper usually, but today I want to be sloppy. There are a lot of a gap gonna be. So everything I wrote today is conjecture, but probably it's true that in every physical literature, every written words there is conjecture. Yeah. Okay. So before I go move on, I want to give another remark is that we take an algebra quantum field theory point of view. By that I mean, so a topological order can be viewed as a TQFT defined on an open disk. So in this case, 2+1D, I really mean D2 times time slice. Okay. So I will consider everything on the open disk as the way I draw it. Okay. So the connection to high energy people, because high energy people like to consider path integral in a non-trivial space-time manifold. The relation between these two is that this is purely local. In order to get the global invariance, you need to do the integral in order to get there. Okay, so so a multi-tensor category is observable on the open disk. If you want a global invariance, so you can do integral. You can do an integral on the surface of a multi-tensor category if you want it. Okay, you can get observable. You can get the global observable. It turned out that this global observable is nothing but ground state degeneracy. Ground state degeneracy. So this theory called the factor homology. I don't want to go to this detail, but I just want to tell you that I'm using an algebra quantum field theory point of view. I'm thinking about the observable on a local disk as the definition of topological order. Okay. All right. Okay, this is the remark. And all right, we'll start from there. Yeah, it's a sigma is a space manifold. Yes. So it's a surface. So yeah, it's a space manifold. All right. So we'll consider, well, you probably, for people familiar with the, or people get used to study topological field theory on the non-trivial space-time manifold, you might wonder, oh, if you restrict only on the disk, do you still have a non-trivial question to ask? Yes, there still are. So here's the theorem that also quite known long ago, I think around this, okay? If you consider a gap boundary, this is 2+1D topological order. In the case that you have a C and the central charge equals 0, chiral central charge equals 0, it's possible to have a gapped boundary. Okay. Let's say gapped boundary. Okay. And on the gap boundary, you also have particles. You can fuse the particles, and this particle, let's say boundary particle. Well, particles on a gap boundary of, let's say, a 2+1D about the order. In this case, this C have to be equal to 0. Form a fusion category. let me forget about unitarity. Okay.
Are there not like empty C's with C equals 0, which are not centers?
Well, this will be the center. That's what I'm going to talk about now. Oh yeah. So this is not enough, but I already assume that this is the gap boundary. I'm going to talk about, yeah, it's the center of the fusion category. Okay, form a fusion category A. Okay. Moreover, the bulk is the dream field center of A. Okay. So, and you can see that the fusion category only have a fusion product does not have rating, because if the particle is confined on the line, you don't have way to braid it. Okay. So, but the relation between this the bulk anion and the boundary is related by this. This is dream field center. Yeah. Right. That's his early comment is exactly just this one. All right. So.
I think the results probably is saying if there is a gap the boundary, then you have two things. One is the chiral central charge is 0.
Yeah.
And another is that the category is center.
Yeah. Yeah.
So see, equal to 0 is the conclusion part, is not the
Okay. So. Well, since you're like people to take notes, maybe I should just rewrite it. Admit a gap the boundary. Okay. Then particle on the boundary, on the gap the boundary, form fusion 1 category A, and this is true. Okay. So roughly it's something like if you have a, so this is the boundary, assume this is the boundary, then you have you also have a boundary particle, maybe xy, okay, and this is also instanton. This is the harm xy, okay. All right.
this figure, what does the vertical horizontal?
No, I just so here's some line in the bulk. Okay, here's some line in the bulk. Okay, you have an anion here. So this is the AB. There's some particle on the boundary. That's the picture. Okay. Okay, so we see that if the boundary is gapped, if the gap boundary, you have a fusion category. Their natural question is, what if we consider a gapless boundary? And do you also have something replace A? That's a natural question, right? And in 2011, when we worked this out, we naturally asked this question, but we naturally dismissed it. The reason is that we thought the gapless boundary is too hard. Okay, we have no clue how to do it. But here comes another progress. Is or 2017 published version. Okay, it says the following. It says that, okay, we do not what this is. Okay, so it says that the bulk is somehow the center of the boundary, even if the boundary is gapless. This is a theorem work for in any dimension. This is work for TO in any dimension. I'm not going to tell you how to prove it. You have to believe me on this. If this is true, if this imply, okay, it just imply, okay, so this should be true. There should be something, okay, there should be something mysterious, we do not know what it is, such that its center equal to this, okay? So it implies there is a universal, there is a unified mathematical theory of both gapped and the gapless boundaries of 2+1D topological order. The good thing about the 2+1D topological order is that the bulk is completely known because this is the multiplicity category. Okay? Yes?
Does gapless mean like a single vacuum safety or QFT?
A single.
Like gapless does mean like a CFT, unique vacuum, or can it also be a QFT?
Can also be a QFT. On the boundary become a gapless, so it's not topological anymore. Yeah, but the bulk is still topological. Bulk phase is still gap. You can define the local gapped property without touching about the boundary. Yeah. Yeah, so if you do not introduce a gapless boundary or try to avoid the boundary, only consider the whole thing on the closed surface, the rest-seeking area of TQFT is well defined without considering the gapless boundary. CFT is a CFT. Gapless, yes. Yeah, we'll get there. Okay. All right. So this is the. But okay. So let me make a remark on, about this. This is known. This is not known. Okay. Let's consider a special case. What about the dream field center of C? The dream field center of C is the famous the double. This is the same multiplicity category except the replace breeding by its anti-breeding. So roughly speaking, it's just C squared. So roughly speaking, you can say the question mark is square root of C. And I want to remind you that the square root problem is always mysterious in the history of mathematics, right? The first one discovered this, it is killed. Okay, this is also famous, but this is, I think this is also well known in physics. Taking square root of Laplacian, you got a Dirac operator. All right, so now we also want to do the square root problem. This problem in mathematics, it was known for a long time. Okay, I think in 90s, quite a few people to raise this question in the middle of 90s, but without having a lot of clue how to do this. One of the early people who mentioned this, I think, is rest-seeking. I'm gonna talk about the significance of this in mathematics at the end of my talk. Okay. All right. So.
You can always just add more particles on the boundary. So the reconstruction of the bulk is not unique. You just add a two-dimensional decoupled Frobenius algebra
to the boundary. Do you mean you just have a 1+1D CFT attached to this? Yeah. Stacking. Yeah.
There can't be a general way to obtain a unique answer in the bulk, given the boundary.
No, you can't. My theory will answer this question precisely. Yeah. I will restate his question is very important because I think Shu Hengshao also asked a similar question many years ago during the COVID. Xiaogang sent a video to me. He asked the following question: if you stack a lower dimensional CFT into the boundary, and this CFT also have symmetry, the category of topological defect line. It has a fusion category symmetry. It will change the symmetry. And what happened to the bulk? Looks like bulk is unaffected here, right? Okay, looks like a puzzle. So today, once you see the complete theory, it will automatically cover the situation, and there's no contradiction. Everything perfect fine. Okay, so we're going to do that. Okay, so in 90s, if you guess mathematically what is the square root of a modular system category, it's hard to have any clue. Okay, but now the Mother Nature provided answer to you, because what this is trying to say here, what this is trying to say here is that what is A? A is again similar to this one. It summarizes all the microscopic observables, right? So what this gonna be? This also gonna be the thing, whatever you got, obtained by summarizing all the observable in a long wavelength limit on a gapless boundary. So we're gonna do this. Okay, what are the microscopic observables on 2+1D worksheet of a gapless boundary of 2+1D. Okay, so this is a natural question we're gonna investigate. All right, let's start from here. Okay, the first observable you can imagine is, okay, let's make assumption here. So the first assumption is that, oh, this is the gapless. Let's make assumption. This boundary is conformal. So the gapless boundary is a CFT and the chiral. To make life easier, let's assume it's chiral. Okay. In the end, we're gonna cover non-chiral case. Okay. Left mover, right mover. Yeah. Assume it's chiral. Yeah, completely chiral. But in the end, I'm gonna jump to, non-chiral case. Okay, so this is the worksheet, 1+1D worksheet. Okay, 1+1D boundary. Okay, okay, what is known in early 90s already? Well, it's a CFT, right? So you're gonna have some chiral fields. Okay, so there is a family of chiral fields living on the worksheet, and they must satisfy the following conditions. So you can do a Laurent expansion of that. And the important thing is that it cannot have any non-integer power, because if you have a non-integer power, you have multi-valueness. Okay, so the field living on the 2 cell. Okay, living in the 2 cell. Okay. The secondly, you can have OPE. I'm using a physical notation instead of mathematical one, just to make the audience, a physical audience, looks familiar. Okay, this is OPE. Okay, and if I use precise mathematical language, is that U is a vertex operator algebra. I would abbreviate that as a VOA. Okay, that's the mathematical statement. So that means if you have a 2 field moving closer to each other, they will have OPE. Okay, mathematics is known that is a VOA. Inside this VOA, there is a subalgebra generated by energy momentum tensor, which is this is a sub VOA. It's a very important later. Okay, and you know that the component of this generate a versor algebra of central charge C. Okay, so that's the first data. This is known. This is known in early 90s, so it's not new. people know this already. Okay. However, if you stay at this stage, you ask yourself, oh, is that order observable? If this is order observable, you have to figure out a way to make sense of, let's replace the question mark by VOA, then the center of VOA have to be multisystem category. It doesn't make much sense. So the natural questions, do you have more observables? Yes, you definitely have more observables because, look, let's assume this boundary is gapless. But remember, in the bulk, there are anyons, right? You can have an anion you push to the boundary, what's going to happen? It become a boundary particle. Or if you have a Wilson line in the boundary, you push to the boundary. The Wilson line in the bulk, you push the Wilson line to the boundary, you become a topological defect line. Okay, so this means that. Oh, I don't need to. I just draw it over there. So beside this, you also have a defect lines. Okay, so not, in general, it's not one, a family of defect lines. Let me put the topological defect lines. So let's say A, B, C belong to a set S. Okay, a family of defect lines. And let's see if I can move this up. Oh, okay. Let's say UA is the space of chiral fields living on the TDLA. Okay, let's label that. Okay, so it's why I use the R here. R belongs to real number. In particular, I prefer to be positive. Okay, so this field can have a Laurent expansion. Okay, let me use this spatial dimension. Let me call this time direction. Okay, and the time direction, I will choose the time direction to be the real number. Okay, maybe it's better this way. If that's the real number, maybe we'll call this x.
R.
Yeah. R is the time direction, the real number. So I want this the field living on okay, maybe oh god, let's say 2. Okay, they can have OPE. So psi R1, chi R2, they also have OPE. But in general, the OPE could be quite wild. R2 plus. Okay, and K here is only a real number. Well, positive real number. Okay, in general. So mathematically, such algebra is not a VOA anymore. Math terminology is that UA is an open string VOA.
How do I see that there are no fractional powers inside?
Well, I'm doing bootstrap here. I'm not giving examples. I just give you a bootstrap. So in general, if you feel the restrict on the line, there's no requirement for it to be have to be a positive integer. But yeah, you don't need, because you don't worry about the market valueness. I assume that because it is reasonable. I'm doing bootstrap. No, in the example, they were definitely going to be correct. But for all the rational CFT, you get this belong to Q. Not integers, yes.
So I'm asking, why are you assuming it's
I didn't assume it's integer.
Oh.
I assume n equal r. Yeah. If you only
n is in R, it's
yeah, here is a n equals z. Belongs to z. Yeah, belongs to r. So if you like a rational case, that's Q. Yeah. Yeah. Okay. All right.
Sum over R, you need sum over integer plus some real number. So
yeah, I don't know.
Yeah.
So
Yeah. It's a subtle, but I think that in the VOA literature, people already assume that there's special meaning of this. You don't choose uncountable sum. Yeah, you
no,
always choose.
usually I think you write, there's a shift up there, you put up there, and then you sum over integers.
It should be
You might,
some
minus n plus some delta.
yeah, it should be some rational
And then
number
you sum
plus
over
integer.
integers. If that's the typical.
Yeah, that's the typical. Exactly. Yeah.
That's a sum over integers. But there's a shift up.
Yeah, it's shifted by some Q. Yeah, in examples. Yeah. Yeah, well, I think roughly it's okay. Belong to Q is not
Just
wrong.
add a
Yeah.
plus delta to change.
Q, you have a special way to write this? Yeah, okay. Or some s belong to finite plus integer or something like this. Yeah, plus it, right? S belong to some finite size. Okay. Okay, that's fine. Yeah.
That the lines necessarily topological in Sept, you can have
Yeah, you can have more, but we don't know how to do that in that case. But in the end, I'm going to talk about it, how to go beyond the setting. Assuming it's topological is just for convenience. You see, we're hoping to find the solution of this. We hope that the topological defect line already give us solutions. But if you consider weaker assumption, yes, they might give more solution, which is open question now at this stage. Okay. Yes.
Question about topological defect. First you have ABC from Sept, and in this dashboard you have anions in ABC. Are they the same thing or different?
They're different. Yeah, they're certainly different. So I also use ABC. Yeah, I kind of get used to ABC. I always start with ABC. Yeah, they're different. Okay, this is in C. This is object in C. This is some kind of unknown object. So I assume there's a family of defect line. I don't know what they are. I just give a finite label. Yeah, at this stage.
On sketch you are telling us like some relation of pulling anions.
Later. Yeah. Right now there's no relation. Yeah, there's no relation. Okay, so
Topological defect line and
I'm gonna talk about that later. Okay, you can ignore the topological for now. Okay, but they have to be conformal in some sense. Okay, but again, this one also have a subalgebra embedded in UA. Okay, generated by energy moment tensor. Okay, this is not only a subalgebra, it's a sub VOA. Okay, itself is a VOA. So this similar to okay, if you're a physicist, the vertex orbital algebra have another name called Carroll algebra. It contains a versor element or energy moment tensor. Energy moment tensor have a OPE generated algebra by itself. That's a sub VOA. Yeah, but in this case, again, it's a similar because this is also generated a VOA, and this is generated a VOA, which is sub algebra of that.
that's like an energy moment tensor on length.
Yeah.
There is no such thing. It vanishes by conformal symmetry.
Oh.
So it's only one component.
Okay. Let's assume it's topological. Let's assume there's a such thing. No, there are a lot of examples. There are, but for the most general one, maybe not.
It's not
Can we talk
conformal line defects or topological line defects do not have a local energy momentum tensor defined. There is no such.
On the
VOA.
topological line defined?
Yes. There is no energy momentum tensor on a topological line defect.
Topological line
If there was, it
defect.
wouldn't have been topological.
Oh, maybe our definition is different. Can I give you my definition later? I don't know what your definition is. Okay, I will show you my definition of topological defect line later. Maybe I'll tell you my definition. Eventually, it will clarify the notation, what I mean. Okay. All right. So I claim there is. Well, I assume I'm doing bootstrap. Okay. You can view this assumption. Okay. There's a subalgebra generated VOA, which is subalgebra of that. Okay. All right. But these are
it's not isomorphic to the ball.
no, it's not. In general, it's, at this stage, we couldn't tell. I'm doing bootstrap. I'm gonna analyze the certain structures. Eventually, I'm gonna tell you what it could be. Right now, I have no idea what it is. Could be.
There could be more operators in
Yes.
this than the ball.
Yes. Yeah. Okay. Oh, the force data. What else you can have? Okay, here's what else you can have. Similar to the bulk, right? You can have a different TDL between. Well, there is an issue about what is meaning of between two different defect lines, and between these two there is a defect line junctions. Okay, so what is MAB? It's a space of field leaving on the junction, defect junction. Okay. And in particular, you can see that UA is just a special case of MAA. Okay, because MAA is the space of field leaving on the junction between A and A, but A and A is trivial junction. Okay. All right, so it tells you that MAA have a OPE. Okay, so MAA have OPE. But what about MAB? Most general OPE. The most general OPE is this. You take, let's take another one here. C, B, M, B, C. Okay. You take a field leaving in MBC. You do a vector space tensor product with this. You do a OPE. After OPE, they fuse to a field leaving in MAC. Okay, so that means you have a field here. You fuse them. You got a field leaving here. Okay. This is the most general OPE. Okay. Before we move on, let me pause for a quick remark. You see what kind of data we already have. We have a set, and we have a MAB, and AB belong to S. And we also have some kind of things like a composition, right? Like a composition. So it's almost a category. Almost a category. Not yet. Okay, so I'm telling you that All right, let's continue. What is the missing if you compare it to the category? If you compare it to the category, you already have that, you already have that, you already have this, but you don't have the unit. So the last one is the unit. So there is the trivial defect line. Well, whenever you have a defect line, that's it's a question mark now. Let's call that 1 or just 1. Okay. What is the meaning of trivial? The meaning of trivial simply means M11 equal to U. Because what is U? U is this one. So U is the field leaving on the 2 cell. Okay. When the defect line is trivial, it simply means trivial means it cannot be distinguished from its neighborhood, right? So the field leaving on the line have to be the same as the field living in its neighborhood, but field living in the neighborhood is U, so this is true. Okay? Okay. All right. Let's consider a defect line. Defect line labeled by A. Okay, labeled by A. Now you have on the one side you have U, a field living on the 2 cell. Okay, you can fuse into it. Okay, but let me call that LA. You can have the field in the 2 cell fuse into this MAA from left. You can also have field of U fuse from right. Okay, here comes my basic assumptions. For this one, I have a subalgebra generated by that. And this one, I have a subalgebra generated by that. And this map, okay, it's a map to, it's a subalgebra of U. Okay. My requirement is that these two have to be isomorphic. Is it isomorphic? Not only that, these two have to be equal. So here's my assumption. Does that, what is called?
Yeah, that just means that the energy momentum tensor of the bulk theory rolled near the length.
Yeah.
So,
Yeah. What do you call this kind of defect? What's the name? How you call this kind of defect line?
No, it's not a genuine energy momentum tensor of the line. It's like what came from the bulk.
Yeah, it came from the bulk. Yeah. Okay. So maybe this clarifies the confusion. Okay. So this is reasonable, right? Okay.
That's the
Yes.
case. That's the case. Then this algebra generated by DR should be factorized. Should be a subfactor of U.
You mean this will be factorized?
No, I meant the ring that's generated by DR should just factorize out of UA.
Factorize the UA. I'm not sure I understand your. So what factorize in the UA? Sorry, can I say it again?
So the ring that's generated by DR, it's
By
obtained by taking an energy momentum tensor and then just placing it on the line.
yeah.
Which to me, it seems to suggest that the ring should just be like closed subalgebra, and the UA should be like something else times the product of the set.
Not necessarily. You could just contain it. I don't know why it's factorized. Yeah, I don't see, from example, I also don't see. Okay. All right. So this is my minimum requirement. You might, okay. But you can also, now I want to introduce something. That's my assumption. Assume subalgebra which is which could be bigger than the smallest one, and could be same as the largest one. That's U. That's M11. Okay, that's M11. But at this stage, I do not know. My assumption is that this V satisfies this condition. Okay, I assume this also embed in it. So the left A, RA. So what I mean, my assumption is that LA restricts on V and RA restricts on V are identical, are the same map. Okay, that's my assumption. That's equivalent to say V is transparent. So V is transparent to the line. Okay, because this V mapped to the line, and there is also V there, and you can freely move away because both of them are isomorphism. This one. Okay. This is I assume, that's my assumption. So V could be this one, but I do not know at this stage. I'm guessing there should be one, could be somewhere in between these two. That's I'm doing a bootstrap. I'm guessing what kind of observable could leave it on the worksheet. At this stage, I do not know. I assume. The largest possible is this one, right? But I'm not sure. From the example you're gonna see later, they are not maximum. What? Exactly. Yeah, it depends. So it means that if I choose their largest is a problem because this defines the topological defect line. If I choose a V small, I will have a lot of defect lines satisfy this condition. If I choose V to be big, I will have less topological defect satisfy these conditions. Yes, yes, that makes sense. If you fix a line, you can ask what is the maximum one that make this condition satisfied. Yes. Yeah, the V right this now, I do not know. So either you can fix a set of TDL, a topological defect line, or you fix a V. You will see how these two interplay in the future. Okay. That's the precise meaning of transparent. So V can move to this as an isomorphism, move onto the line, because this is leave on the line, right? Onto the line and move out, because this is also isomorphism. No, it's in the vertex operator algebra. I'm not sure in the phenomenon algebra is that commutant or not. You have to smear out the vertex operator in order to get the phenomenon algebra. I don't know how. Yeah. Yeah.
So you can single out those which you do left and right. Say that's here it shows B.
Can I say yes or no? I tend to say yes, but I'm not entirely sure this way of formulating it. The way you formulate it make me a little bit hard to say. You see, I'm doing a bootstrap analysis similar to Morris-Iverg. So I'm guessing what kind of, so at this stage, I do not know what happened on the worksheet. I can only analyze what could happen on the, so I will try to make as less assumption, I try to make less assumptions. So this V could be just this, or it could be something. So right now, I didn't say anything. I didn't say V is not this. Could be just that. Okay. But in general, so if in a lot of rational VOA, for example, WZW, if you restrict to this condition, this VOA is too small. And if you work with that, the TDL will explode. Okay. So so very often we're gonna assume much bigger V, or even for convenience, we assume V is rational. You know, later we're gonna do that. Otherwise, we cannot proceed. You know, that's the problem. All right, V is transparent to the line. That's the meaning of that. But this heuristic statement is useful for us. Okay, can I proceed now? Or questions? Feel free to ask questions. I really want people to understand this.
The other way around?
Yeah, well, V, you say the other around would maybe equivalent because they're interplay because if I fix the line, if it fix the topological defect line, there will be a maximal V sorted to it as is common. But if I fix V, you can also, what is the maximum amount of a line that satisfy this condition?
No, sure, but I would just consider the line the thing that you endow with transparency rather than the operator. You would call the operator penetrable or something like that. It's just terminology.
Okay. Okay. Yeah, that's just, this is the terminology. Well, this is V is, you know, penetrable to the. Yes.
Generally, I think bootstrap.
Yeah.
Suppose you don't need examples, but suppose.
No, we will give you example later.
should I keep the Fibonacci category or Easing category as an example and try to translate everything to that content?
Only after I finish the bootstrap. You see, the problem is that, you see, I think that's the reason why we didn't even do it at this stage after we finished that work. We thought about the gapless, but it seems to me just too complicated. There is no hint of what to do. You see, in the end, this will be our guiding principle. Without this guiding principle, we won't be able to solve this problem.
Am I allowed to ask
Yeah.
Easing category, what are the set of
Later. I'm gonna tell you later because, you know, if you see, this kind of problem is this. If you directly work with example, you see, from this analysis, it won't tell you much more information. You know what I mean? Because you don't even know what you're looking for. You start with, okay, so I can, for example, later on, I'm gonna also give you, you can say, well, this summarizes all the microscopic observable, right? There is an immediate question I asked Xiaogang when we start to collaborating it. And okay, what about the symmetry breaking phase? Within the Landau paradigm, right? You can ask this obvious question. But we don't know how to do it. For 10 years, we have no clue at all because we do not know what is observable. Okay, just for example, just give me an Ising chain. We tried, okay, when we started all this, we tried to describe Ising chain. We failed. We don't know how to answer this question, even for the simplest lambda phase in the lambda paradigm. But today, you will see the solution to that. Okay, can I? Oh, more questions? Feel free to ask questions, yeah. All right, 8. After some, yeah. All right, this statement immediately tells you something. AB is equipped with a 2-dimensional V action. Okay, here's V. Okay, here you have U. V is a subalgebra in this. Because the line is transparent, so you can axon field here doing OPE. That's an action. Okay, you can also rotate it 100 times, then X. The transparency tell you, well, these two should match. If they don't match, they should interfere each other. Something gonna happen. So okay, so you should have a 2-dimensional V action. Mathematically, this just equivalent to say because the mathematical definition of a module over a VOA is exactly 2-dimensional action, if you're familiar with VOA's modules definition. But if you don't, you have to trust me on that. Okay, the VOA module over a VOA, or equivalent. Yeah, you can do both, but they're analytic continuation of each other.
Yes.
Yeah. So I don't want to go to the math of VOA, but if you want to check the axiom of a module of a VOA and why this is corresponding to the two-dimensional V actions, we can do that later, because if I do it now, it will take another 40 minutes. Okay, VOA is too much. I didn't even record the definition of VOA, so I avoid everything with VOA. But I want to make the logic very explicit. Okay, so that's 2. Okay, it's a little difficult for me to write in that, so let me erase. Oops. Uh-oh. Okay. Next. We're not done yet, but close to. Okay, what's the next data? 8. So the next one is BC vector space tensor product with AB mapped to AC. This is about OPE. Okay, this OPE is compatible with V actions. What do I mean by that? What I really mean is this. MAB, MBC, here's a V, okay? So you could have, so there are 3 ways to do this. Do the fusion. You can have an OPE with this, or you fuse this two first. Then you fuse this two first, okay? So you first do that. There is one way of, so I'm gonna tell you 3 ways of fusion. Probably I probably don't, okay. Let's do it. There's something like this, something in here, BC maybe, AB here. Okay, so I first do a OPE with this. Okay, then I will do a OPE with this. Another is I first do a OPE. I first do a OPE with VX on AB, then do a OPE with this one. The third one is, okay, I can do OPE of this two first, then do V. The 3 are compatible. Okay, if you write down this properly in a precise mathematical language, it just tells you, okay, this OPE is this one, this map, this OPE map is an intertwining operator of type. Remember they are all modules. They are all V modules. So they are of this type. This is notation already in Morse-Seiberg. This is also standard in physics, in mathematical literature, over V, over the VOA. V. These are V modules, okay? Intertwining operator defined of this type. You have to trust me on this because this explaining this take another hour, even longer than the other one. Okay, all right. Then by the theory of Huang and Lepofsky, I think it's around the okay. Let me translate everything. So this is equivalent to say there is, I'm gonna do a magical move here. Previously, this is the vector space tensor product. Okay, now I change it to relative tensor product over V, because they are V modules, okay? So this makes sense. V module map. To say there is an OPE satisfied, which is compatible with the V action, is equivalent to say this OPE map define an intertwining operator. But mathematically, you can also prove that this statement is equivalent to say there is a map canonically defined by OPE. I will call that composition, this map. And this map is a V module map. What does this mean? It means it is a morphism in mod V. Okay. Now we can draw our first conclusion. let me summarize. Theorem, summarizing the, so you have a set of labels, right? Then you have MAB, AB belong to S, okay? And you have, for each MAA, there is a canonical map. Look, this map is canonical in the sense that it's path independent, okay? Because the left, if you do it from left or right, are the same. And the third one is the composition. Let me, BC tensor V AC AB map to, there is a composition map. Okay? Okay, putting all of these together form an a category enriched in mod V. Enriched category is defined similar to the category. It's okay. Let me give a notation for this. Okay, let me just call it in order to simplify notation, and for the later reason, let me give another simplified notation B. Okay, enriched in B. B just mod V. Okay, let me denote it. Let me denote it by a strange notation. Will be clarified later. Okay, this is just represent the enriched category. So what is the data of the enriched category? It simply tell you the object in the enriched category is just a set. Okay. Second, the Ham space of the category is defined by MAB. But remember, MAB is the object in mod V. Okay. The third data is the composition of S, AB, BC. Okay. Now you do a tensor product in B, because previously I used over V, but now I already replaced that by an abstract category. So I want to express everything abstractly. AB composition, BS, AC. Okay, everything is, so this is a morphism. So this is a morphism in mod V. Everything is living in mod V. That's the meaning of enriched category. A little bit over. I don't know. Can we? I will write down the main result now. And if but yeah, I will write down main result now. I could stop there, but if you want to hear more, we could continue. Yeah. Yeah. Or anyone want to leave? That's fine. Okay. Did we finish all the data? No, not yet. Okay. Yeah, that's what I'm going to talk about. That's what I'm going to talk about. Where is that picture? Yeah. Okay. There's the last missing picture, exactly what Kevin said. So you can have TDL here. Let's say Q, and this is P. Okay, and you can fuse this two. Okay, when these two lines getting closer, you really fuse them into one single line, A tensor P. Okay, so the horizontal fusion. Okay, so that means, you know, as I showed here, A tensor P. Okay, upgrade. Well, what? Upgrade to a B enriched That's another terminology. A category enriched in B, or I can also call, or another name, popular name is that we call it the B enriched category. Okay. So we upgrade this, but this is just a category. Now we upgrade it to a B enriched monoidal category. Okay. Now we can say the main results. Uh, 2007. I was told this seminar usually is 1.5 hours, but mine has become 1. Okay, but I think it's not enough. But anyway, I'll say the main result and see how it goes. Okay. So this theorem says that, what is it? Let me put something I probably need to add in here, but a gapped or gapless boundary of 2+1D topological order CC can be completely characterized by a pair where now I'm gonna moving forward. I'm gonna jump a lot of steps. So V is so a rational VOA. That's where the something I should add in here. I could add a rational. Well, it depends on what that means. What do you mean rational boundary? But it's confusing. But this really refers to this rationality here, okay? Or for condensed matter, maybe some people can also call the liquid-like, but like a quantum liquid. But anyway, so it's up to you. But the real meaning is here. If the boundary is chiral gapless, okay, and the V is rational VOA of central charge C, of central charge C, okay, a rational full field algebra. What is full field algebra? It's a chiral analog, a non-chiral analog of VOA. You can just view it as a non-chiral VOA, okay? But it's non-chiral. If the boundary is non-chiral, okay? If the boundary is gapped. Okay. Where's my? Oh. Oh. Well. The second data, V is just mod V, which is a multi-sensor category. By that assumption, rational VOA, rational full field algebra by definition also just means the mod V is a multi-sensor category. Okay, and and S is a fusion category equipped with abraded equivalence this is a dream field center. Dream field center. Okay. B is changing the braiding to anti-braiding. Okay. As a consequence, B acts on S. Because B maps to the dream field center, but the dream field center acts on S.
So B plus mod V you already introduced before, and then you're saying parentheses MTC. No, sorry, the line above.
Yeah.
You're just
It is a
modular.
yes. It is a modular sensor category. Okay, mod V is a modular sensor category. Yeah. Okay, so well, B acts on S, so S is a B module. As a consequence, there is a notion called the internal harm is defined. I'm gonna comment on this later, but once you have that, then we obtain and B enriched category, fusion category, such that the object is the same as the object in S. The second harm, the harm space is defined by internal harm. Is the object in B. Let me give a remark. How the internal harm is defined, I won't define it today, but I want to give you a defining property, which you can use this to if you have an action on X, this is the defining property of internal harm. Use this. This already determined the notion of internal harm. So internal harm is defined by this property. Once you have so A is what I mean by that. A belongs to B, X, Y belong to S. Okay, for any A in B, any S, Y in B, this defines the internal harm. So this defines a enriched category. Okay, that's the end of the statement of the theorem. Okay, the punchline is this theorem. C that's our original goal. So this means theory is BS can be constructed as an enriched fusion category. It's a dream field center. Of course, the notion of dream field center need to be you have to redefine it properly. Okay, yeah. But there's no degree of freedom because the notion of center satisfy the universal property. Have to satisfy universal property of notion of center. The only trick is that you choose proper two category to work with. Then you get this automatically. Okay, so example. You probably find this very abstract. Yeah. Rational just means that I assume V is rational here. If you drop this condition, yeah, this is the chiral algebra. So rational just means mod V is a VOA, or a modular sensor category. The same as Morris-Seiber. A chiral algebra is rational if mod. Yeah, that's the chiral algebra. Yeah. Yeah. When I give you example, then it become okay. So for example, you choose. Yeah. Okay. Yeah. Maybe it's time to stop in here, even though
Thank you so far. Thank you.
Thank you.
Quick questions, and we can have a short break, and then we can look at the example for those who want the example. Think. Great. Are there more questions now?
There was this U around in the beginning. I'm not disappointed.
Yeah, because U is just M11. Yeah, that's a good question. Because U at the very beginning is the right. V itself, U itself is a could be VOA. Yeah. Yeah, but U is M11, so it's already encoded in this data. What do you mean more structure? It's a VOA. It's acts on a lot of other things.
One I can only use along the line, right? Where U I can just use in the complex.
Yeah, I know, but yeah, but turn out the one is trivial one, so U is there is no. So M11 priori it is an open string VOA. It's an E1 algebra, right? But because one is trivial, it in this case it becomes E2, automatically E2. I think it's similar to the following. This is similar to the following things. You have a E1 monoidal category. You only consider tensor unit. Oh, wait, if you consider any object, you consider endomorphism. That's again E1. But if you consider tensor unit, you consider the endo of the tensor unit, it automatically E2. Right?
Yeah, I agree with that.
Yeah. So this is M11 is the endomorphism, some kind of a observable leading on the trivial defect line. That's looping. After you do looping, it becomes E2. Is it topological in what?
I can move the line and nothing should change.
Yeah. Yeah.
Here is in the C I should not be. Anyway.
I'm not sure I'm not sure I understand your.
More questions?
So I mean, I'm not an expert in this at all, but somehow this data, from what I understand from condensed matter people, is enough to find some 3+1D commuting projector model. Do you know anything about this, or
this is something I want to comment that this open a way for you to to construct a lattice model for chiral topological order. Well, for example, you can see in the level 1 model. In the level 1 model, what you label a vertex is by the harm of the fusion category you give, right? Well, this suggests that this doesn't work. What you have to do is you have to replace by infinite dimensional vector space, which is internal harm, leaving in a vector mod V, for example. There are people who already do that. For example, Ingo Runkel produced one called the inner level 1 model, in the sense that you can still treat it very topologically. However, inside this model, you see you have another one. When you do the tensor product, you do not do tensor product in the vector space, right? You see what happened here is yes, this thing, if you tensor in a vector space, it's really wild. But if you tensor over a V, a background looks like, then this thing makes sense. That's recently, I think Ingo, you called it the internal level 1 model.
We have worked on design infinite dimensional space of objects in the category.
Yeah. Because the infinite dimensional space now, MAB, become an object in the non-trivial category. So you replace, previously it's a finite dimensional vector space, now you replace by internal harm. The internal harm is infinite dimensional because it's an object in, because it is an object in mod V. So it's a V module, it's infinite dimensional in some sense.
It's a very pedestrian level, like an actual 3+1 dimensions. So you discuss 1+1D, 2+1D. They're just a pedestrian level in which 3+1D.
3+1D. 3+1D, yeah. But are you saying that can you, because modular tensor category on the 3+1D level is invertible, right? and the multi-system category is a 3+1D, 2+1D boundary of that one, right? So are you asking, are there any story of 3+1D TQFT and down to this one? Is that what you're asking?
Yeah,
or?
I mean, I thought the data here was enough to define 3+1D generalization.
Exactly.
but when-
Exactly.
but
Exactly.
I just don't.
Yeah.
I'm not an expert at all. I don't see how
Yeah.
that fits in.
It's by David Pennies. He already written it down. So what do you do is generalizing worker one. Kevin was here. So what they do is that they use this B to decorate the 3+1D block. And they use this one to decorate the 2+1D boundary. You got a generalized worker one model. This can be further generalized by considering streamline model in 3+1D. But that will be another lecture. That's not planning to go there yet, but it's a good question.
Break, and then
Yeah.
we can see.
Okay.